the topics for the final exam. This is summer 2018. What a great semester it has been. All right, let's end it on a good note. The first topic is capacitors. And the basic definition for capacitance is it is the ratio of the charge to the voltage. Of course, the unit of charge is coulomb, and coulomb divided by volt gives you farad. So that's capacitance, basically. Okay. And for a parallel plate capacitor, K epsilon naught A by D is the formula. K is the dielectric constant, just a number, no units. Epsilon naught is the permittivity of free space, which is 8.85 times 10 to the negative 12. A is the area of the plates, assuming that both have the same area. But if both do not have the same area, then A will be the overlapping area of the plates. A will be the overlapping area. D is the distance between the plates. So to increase the capacitance, increase all the factors in the numerator, decrease the denominator. That means get the plates as close together as possible, which is a dangerous situation because then there is a chance of sparking, and that's avoided by using a dielectric, right? So that's why we have a dielectric. Also look at the uses of the dielectric, please. That will be something conceptual there. And like I said, capacitance is in farad, coulomb per volt is farad. K is the dielectric constant, and K for air or free space is 1. Okay, epsilon naught is 8.85 times 10 to the negative 12. That's the unit of that. That is topic number 1. And also you have capacitors that can be connected both in series and in parallel. So 1 over C, do not forget that what you have on the left side is 1 over C. And also remember that this formula is exactly opposite to the combination of resistors, right? Parallel and series. Another important concept here is whenever capacitors are connected in series, the charge across them will be the same. Capacitors in series, charge will be the same. Capacitors in parallel, voltage will be the same. In fact, any electrical component in parallel, voltage will be the same. So that is energy of a charged capacitor. All this is about a capacitor, as you can see. Energy of a charged capacitor can be written in 3 ways. These are the 3 formulas. So you can have them in these 3 ways. Topic number 2. Resistances. The idea of resistance comes from Ohm's law, where resistance is voltage by current, right? And then resistance depends on the length and the area of cross-section. Rho. What is rho called?
Charge density.
Rho. No, not in this case. What is rho? Resistivity. Resistivity. Remember that if a conductor is stretched to double its length or triple its length, remember that the resistivity does not change because resistivity depends on the material. Resistivity depends on the material. But would the resistance change? Yes, if you stretch a cable, the resistance would change. Be careful on that. Now, again, A is the area of cross-section. So assuming a circular cross-section, A is pi r squared, L is the length of the conductor. A combination of resistances, it's exactly the opposite formula. So if it is in series, then R is R1 plus R2. If it's in parallel, then 1 by R. Again, take note, left side you have parallel. And you also remember that there is an easier method to do it. If you only have 2 resistors connected in parallel, then you take the product divided by the sum. Okay, another important concept here is whenever resistors are connected in series, the current flowing through them will be equal. Current flowing will be equal. And in parallel, of course, the voltages will be equal. That is topic number 2. On to 3. This is a favorite. LRC circuit, series resonance circuit. We also did this lab. So you have to know that inductive reactance is 2 pi f times the inductance. Capacitive reactance is 1 by 2 pi f times the capacitance. And the impedance in an LCR series circuit is square root R squared plus XL minus XC whole squared. That is the phasor diagram that gives you an idea of how they look like, XL. And I just put it, Eli loves ice. And you know what that is? That is just to, focus on the inductor. The EMF comes before the current. So the voltage leads the current by 90 degrees. The voltage leads the current by 90 degrees in an inductor. But look at a capacitor. See, here is for a capacitor. The first letter is I, which means the current leads the EMF by 90 degrees. So that's something that you can use to remember that. Okay, so that's the phasor diagram. And the phasor diagram helps us to find tan theta. Of course, from this diagram, tan theta is XL minus XC divided by R, isn't it? Okay. The resonant frequency in this circuit is given by 1 by 2 pi square root LC. And at resonance, you have to know, this is a concept, at resonance, you have to know, what do you know about XL and XC? They're equal. So if they're equal, then they cancel out, and then you have square root of R squared, which is R. So at resonance, the impedance is minimum. The impedance is minimum and equal to the resistance, which means the current is maximum, right? And that maximum current is given by just dividing the applied EMF by the resistance. Okay. So that's topic number 3. Number 4. You've not been tested on this topic, so be careful about that. That's for sure a question. Double slit interference. Little d is the distance between the two slits. L is the distance between the slits and the screen. The path difference is given by this distance, right? Whatever we call it, that's the path difference. And from the trig there, you get path difference is d sine theta. You've written it so many times. And y is the distance of that point from the center of the screen. That's what y is. So BC is the path difference, and BC is d sine theta. But also sine theta is y by the distance. Oh. Remember that actually it's tan theta, isn't it? It is tan theta. So if you use tan theta, that will actually be better. So, but in this case, remember theta is small. That's why we are able to, take, instead of tan, we're using sine. But we cannot do that for diffraction. Remember that. Here, you're talking about a small space on the screen. But it's always better to have it as tan. So for brightness, we get this condition. For brightness, the path difference should be equal to m lambda. And from there, putting them together, you get this important formula. Relating y with the order where m can take values 0, 1, 2, 3, you know that? And then you know what these stand for. I've already explained that, okay. For darkness, double slit, for darkness, the path difference has to be equal to m plus half lambda. Or you can write it as 2m plus 1 lambda by 2. Same thing. That is interference. All right, going back to the first topic that we studied, may have slipped out of your minds. So traveling waves are also called, can somebody give another name? Traveling waves are also called progressive waves. They progress, they go forward into the material. So the representation of a traveling wave is given by y is equal to a cosine kx minus omega t. Y is the displacement along the y-axis, of course. A is the amplitude. K. I'm trying to slow down because this is a topic from the very beginning. Okay. K. What is K called? K is 2 pi by lambda. Remember? Wave number. K. Omega. Angular frequency. Omega is 2 pi f. All right. I think I'm writing those down. K is 2 pi by lambda. Omega is 2 pi by t or 2 pi times f because 1 by t is f. So when you plug that back in, you get that formula. And then if you divide, does anybody remember what you get if you divide omega by k? If you divide omega by k, you get the velocity, which is what I'm proving now. If you divide omega by k, the 2 pi's cancel out, you get lambda by t, which is the velocity. So conceptually, it's important to know that velocity of a wave is the ratio of the angular frequency to the wave number. That's what I'm trying to say. So that's a traveling wave. Okay. How do you get... Oh, I thought I was talking about standing waves. It's coming on the next slide. So from there to sound, and sound, let's focus on the intensity of sound. Intensity of sound is measured in a new unit, right? Practical unit, which is decibels. Actual unit should be watt per meter squared, correct? And then you have to know how to change from one to the other. This is how you change. Where beta is in decibels, I is in the conventional units of watt per meter squared. This is the threshold of hearing. So if you're given any I, you should be able to get it in decibels. And the 10 here is because of the deci part, right? DECI, 1/10. Okay. Intensity is also P by 4 pi r squared, which means when sound travels out from a source, it has a spherical wavefront, and that's the surface area of a sphere, if you can see, right? So that's the power of the source. The power of the source. This is the distance away from the source. That's the intensity at that distance. Clear? All right. Just explaining that I is in that unit. There you go. Doppler effect. Doppler effect. Study it your own way, but this is the formula that I've given you. Does anybody remember the standard of how to set this up? The direction of sound waves towards the listener is taken as positive. That's the important thing. The direction of sound waves towards the listener is taken as positive, which means if you get it positive, you do not change the signs. If you get it opposite, you change the sign, okay? I think I'm trying to show one here. So if that is the source, and the source is moving to the right, sound waves are moving in all directions, but we draw it towards the listener. So that's the listener. So that's why I've taken this as the reference. So that direction is positive, which means the source is moving in the positive direction. The listener is also moving in the positive direction, which means the signs will not change. Okay, that's what I'm trying to say. So in that case, the formula will remain the same. I've just given one example there, and we've talked a lot about this, so try to get that. Standing waves or stationary waves. How are standing waves produced? Standing waves are produced when a traveling wave moving in one direction is superimposed on a reflected traveling wave moving in the opposite direction. So you have two traveling waves, one moving along the positive x-axis and its reflection moving along the negative x-axis. When both are superimposed, you get nodes and antinodes. And this is the formula for standing waves set up in a stretched string. This was our first lab, wasn't it? Yeah, this was our first lab, where you had those the string vibration and all that. So that's a standing wave. And that, how much of a wavelength is that? Half a wavelength. So that's half a wavelength. Node to node is half a wavelength. Remember that. So that's lambda by 2. All right, so that's how you get, if you take the length, you set it equal to lambda by 2. But here there are some, okay, F is the frequency, correct? That's the length of the string, Ft. What's Ft? Tension must be in newtons, so it has to be kilograms times G, mg. And mu is called the linear density. What do you mean by linear density? It is the mass of 1 meter of the string. Again, linear density is the mass of 1 meter of the string, which can also be found out using this formula, where r is the radius and rho is the mass density, so the actual density. So you can find mu like that. On to electricity, electric fields. How is an electric field defined? An electric field or intensity of electric field is the force acting on a +1 coulomb kept at any point. So from that definition, you get this. E is F by Q, and that is, if it's a point charge, you can get the formula as E is equal to KQ by R squared. Okay, for a point charge. So remember that's a vector. So if you have a distribution of this, you have to take the vector sum. Remember that. But electric potential is it a vector or scalar? Yeah, keep that in mind. Electric potential, easy. Just add it up. Look at the sign of the charges. But this one is a vector, so be careful about that. Okay, electric field due to a plane sheet of charge. We got this formula by applying Gauss's law. Does anybody remember this formula? For a single plane sheet of charge, what is the electric field intensity? Sigma by 2 epsilon naught. Okay, that's for one plane sheet of charge. What is sigma? It's a Greek letter, I know that, but what is it standing for? Linear density is lambda. Sigma is the area density, what you said first. Yeah, charge density, which means sigma is total charge divided by area. Total charge divided by area. When you prepare for the exam, you have to focus on each term. Look at how you can get that. Look at its units. That's how you prepare. All right, if you have two plane sheets with opposite charges, then you know that the field on the left side and on the right side will be 0. But between the plates, it will become double this. And so that's for a single infinite sheet of charge. And if it's 2, then it becomes double that. So it becomes sigma by epsilon naught. So you have to know the difference. And that's how you get sigma by epsilon naught, by adding both. I'm trying to say that outside the electric field is 0. Inside, between the plates, it's sigma by epsilon naught. You see the two arrows? Both contribute equally to that, and that's how you get that. All clear? Okay. Internal resistance. Every source of EMF has an internal resistance. So if you have a simple electrical circuit like this, and you have a cell, it's going to have an internal resistance. Is this the internal resistance? No, that's the external load connected. So the internal resistance is assumed to be a small number. There you see the internal resistance now. Currents always flow from positive to negative, and by simply applying Ohm's law, you get E by R plus R. And the voltage across, here is the point. The voltage across the load, will that be the same as the terminal voltage? Will that be the voltage here, is my question. So if I connect a voltmeter here across the terminals of the battery, or I connect a voltmeter here, will they both show the same reading? The answer is yes. Because electrically, this point is the same as this point. And we've talked about this. You don't have anything in between, do you? No. So the terminal voltage is the same. And the terminal voltage is given by this formula. Now, don't be confused. This is the voltage across the load, isn't it? Which I just told you is exactly the voltage across the terminals of the battery. That's one point where students always get confused, so keep that in mind. So you can use that formula to find the internal resistance, okay? This might be a repeat. Yeah, we talked about combination of capacitors and resistances. I just wanted to compare them, right? You see that the formulas are opposite. Sometimes I've seen students go wrong. Please take your time, read the question, decide whether it's about a capacitor or a resistance, and then move on. Magnetic field, okay, magnetic force rather. This is where the cross product comes in. So you need to prepare on that. What's the formula for the force? F is equal to Q V cross B. V cross B. Okay, so you need to know how to take the cross product, and I took the simplest example to save time and to show you how to take a cross product. You have to set it up in the form of matrices, right? And take that, IJK, 340. Remember, it should be V cross B. So put the coefficients of velocity first. Am I right? And then for the magnetic field, why only 5? Because it's only 5K. And then take the cross product. So spend some time on that. Make sure you understand how to do that. Okay? In this case, you're going to get 20I minus 15G. So remember to study how to take the cross product. And remember the rules. A rule is given by the right-hand rule, correct? For the force acting. Okay, prepare on that. The stretched fingers give the direction of? And then when you bend it at right angles, it gives you the direction of the magnetic field. And then the thumb will give you the direction of the force. Yeah, we've taken some time on that. All right. Electromagnetic induction, Faraday's law. E is negative d phi by dt times n, where phi is the magnetic flux, and magnetic flux is B dot A. All right? Oh, here there is the way the angle is taken. Do you remember how the angle is taken? I don't know. Do you remember how the angle is taken? You have to be careful about that. Could have a conceptual question. The angle is not taken with the surface. It's taken with the perpendicular drawn to the surface. So, if you have a magnetic field this way, and this case, what's the angle? 0. Remember that. This time, the angle is 90. Just, okay. And then, self-inductance comes in, minus L di by dt, where that is self-inductance. Where phi is Li. Okay, so that's the inductance. So it can be defined as phi by I, and the unit is Weber per ampere, which is called Henry. Okay, so that's electromagnetic induction.
What's the N in that formula again?
N is the number of turns. N there is the number of turns of the coil. And for a generator, you are going to get this. That's the representation of alternating EMF, where E naught is the maximum value, right? Maximum value is given by NBA omega. N is the number of turns, B is the strength of the magnetic field, A is the area of the coil, and omega is the angular velocity with which the coil is rotated. So that much about electromagnetic induction. CR circuit is one of our labs, right? And charging, the formula is given by QM, 1 minus e raised to minus t by CR. Discharge, the formula is not the same, it's without the 1. LR circuit, although we didn't do that lab, the formulas are similar, except that this time it's the current growing instead of the charge. And so look at the difference here. Again, for decay of current, you have a similar formula without the 1 minus. So that's for a CR and LR circuit. So try to work out some problems on that, and it should be pretty easy. Okay. So that's about CR and LR circuit. Wow. Kirchhoff. Can't forget Kirchhoff's law. Okay, Kirchhoff's laws. There was a individual YouTube video prepared on that, remember? Go back and look at that. And here, just trying to refresh this. Let's see. In this circuit, if I look, I can't remember which one I looked at. Maybe A, B, E, F, yes? A, B, E, F, A. One last time, can you apply it? A, B, E, F, A. We always decided to go clockwise, right? Isn't that true? We decided to go clockwise. I think I have the arrow there. Yeah. So if we are going clockwise, and if we're starting from here, or maybe here, start from here, you're going against the current, right? Against the current. Would against the current be positive or negative?
Negative.
Huh?
Negative.
Against the current is negative? Oh, okay. Against the current is negative. I know, you can do it, yeah, you can do it according to your rule. I took it as positive here, plus 5, because you're touching the positive terminal first, remember that? You're coming to the positive, so it's plus, and then you have, yeah, you're going opposite to that current still on R2, and then you have a minus because you're touching the negative here. So take a look at that. This is not time enough to look at that. So you can have it different ways. Mirrors and lenses both have the same formula. And you've done better on mirrors and lenses and optics. So I thought I should include that. DO is the object distance, DI is the image distance. One thing you have to remember is if it's a virtual, if any distance is virtual, it's going to be negative, correct? Except when it comes to magnification, because magnification already has a negative sign there. So just tell me, if it's a real image, is magnification going to be positive or negative? Negative. If it's a virtual image, it's going to be positive. That's the only time there is a change. And then remember that F is positive for a convex lens and for a concave mirror. They both have the same property. And F is negative for the other two, which is a concave lens or a convex mirror. So if you remember that and these rules, that should be pretty easy. Okay, so that is mirrors and lenses. This is our last topic, right, that we just did. Yeah, diffraction at a single slit. Remember, isn't this where the condition changes? Right? So what is the condition for minimum? D sine theta is equal to, come on. Correct. I was trying to show that D is now, caps D is now the width of the slit. Okay? Tan theta is again. Now this time you cannot say sine theta. You have to say what? Tan theta, because it's a bigger angle. Okay? You did this on the lab, right? And you were using tan theta. So remember, when it comes to diffraction, it's tan theta. If you're confused, keep it as tan theta for both. It'll work. So that's diffraction at a single slit. Grating, just did the lab. That is the grating law. Sine theta is equal to nm lambda, and you took the quiz too, so you should remember n is the number of lines in 1 meter, and isn't it? And it's 1 by d. 1 by d is how many lines? The width of one line. Oh, let's take that. So everybody's clear with that, right? Okay, so that's diffraction grating. Resolution or resolving power. Theta is not the resolving power. I mentioned this yesterday. Theta is the limit of resolution. And it's given by 1.22 because of it being a circular aperture, right? D is the, what is D? Okay. And lambda is the wavelength, of course, used. So resolving power is the reciprocal of that. Resolving power is the reciprocal of that. So if the limit of resolution is small, then the resolving power is big.
You should do like 5 or 6 of those.
Of the
Wait.
all right, wait. Okay.
Alright.